All right, so we are getting into chapter 11 today. So this was the chapter that I really wanted to get to before the state assessments because there's a lot of this kind of stuff that I think you'll probably see on the state assessment. Chapter 11 is about volume and surface area of figures. So we're just going to kind of talk about three-dimensional figures today. Talk about some of the vocabulary of the different parts of them, and then we'll get into surface area. All right, so what we have here, we have a three-dimensional figure, but the actual name for a three-dimensional figure is a polyhedron. A polyhedron, that's the official name. Now, it's a three-dimensional figure whose surfaces are polygons. So, like if it had these weird, like curved things for faces, that wouldn't technically be a polyhedron. Okay, so it has to be polygons for the outside surfaces there. Now, when we're talking about a polyhedron, there's kind of three big things we're going to focus on today, and they are the vertices, the edges, and the faces, which are really kind of just what they sound like. Vertices, we've talked a lot about vertices with our figures. So if I wanted like the vertices of a triangle, it'd be the points of the triangle. It's where the sides meet. So the vertices of a polyhedron, kind of the same thing, but it's going to be where it comes to a point, almost. So right there, that would be a vertex. D, that would be a vertex. E, F, G, all those would be vertexes. Okay, all of those are vertices. And if I wanted to name them, vertices are points. So we name them just with one letter. So all of the vertices here would be D, E, F, G, and H. D, E, F, G, and then H at the top there. So the vertices are just points. Now the edges are just like what they sound like, right? If you're looking over the edge of a cliff, right? It's kind of where the turns are. It's going to be where the faces meet. Okay, so we can kind of point them out here. The edges would be like that right there. This right here would be another edge, or the two back edges right there. Those would all be edges. But if we look even closer, that front right there is an edge. And so is that side, and the back. Okay, so there's actually 8 edges there. Now, if I wanted to name the edges, what kind of geometric figure or thing are the edges? Segments. They're segments, right? So if I wanted to name them, we would name them by their endpoints. So if I wanted to start with these 4 that are around the edge of them, we could call one HD, and remember whenever we name segments, we put a little line over the top. We could do HE, HF, and HG. So that would be the 4 edges coming down, but then we would have the 4 edges along the bottom as well. We would have DE, EF, FG, and GD. All 8 of our edges. Okay, then lastly, the faces. So it said in the beginning of polyhedron, it's a three-dimensional figure whose surfaces are polygons. These surfaces are the faces. So I can't really color in all of the faces because that would be like the entire figure. But to kind of show you what I mean, one of the faces would be this bottom right here. That would be a face. Okay? But I also have all of these faces that make out the side. So it's going to be the flat surfaces, the flat planes that make up the figure. So if I start by naming the faces, okay, we're naming polygons. So that bottom face is what kind of figure? Looks like a square. To be totally safe, since you don't know for certain it's a square, it might be safer to call it a rectangle. Okay, so I need all 4 vertices to name that. So one face would be D, E, F, G. And then the other faces, right, are these ones on the outside here. What are all of these other faces? Triangles. So we would have triangle HDE. We would have triangle HEF. We would have triangle HFG. And we would have triangle HGD. And we know right now that there's other ways to name these. You could mix up the order of those letters, but just one way you could name all of those. That's one thing you're going to be doing today, identifying faces and edges and vertices. Okay, now, moving on to another application of all of this, we have this thing called Euler's formula. So there's this guy named Euler, and he discovered that there's this formula that has a relationship between all the faces, the vertices, and the edges. And that formula, and it works for any polyhedron. But the formula, if you take the number of faces plus the number of vertices, that will be equal to the number of edges plus 2. So to show you that that works here, the number of vertices, there were 5. The number of edges, we named 8 of them. And the number of faces, we have the bottom one, and then those 4 around the side, we named 5 of them. So Euler's formula says if you take the number of faces, which we said was 5, plus the number of vertices, which was also 5, it will equal the edges, which we said was 8, plus 2. 5 plus 5, 10, equals 8 plus 2, also 10. So we're going to see through a couple of these that formula is going to work for all of our polyhedrons. So if I go down here, we have another one. So for this polyhedron, let's start with, we are going to decide how many vertices, edges, and faces that it has, and then we'll use those results to just verify that this formula works. So let's start with the vertices. The vertices. Remember the vertices, these are like the points. They're going to be where the edges meet. Where the edges meet. So I kind of like to start at the top of the figure and work my way down. So if I look at the top here, the edges would be like that point right there, right? Where the edges meet. And then right here, and right here, and right here, and right here, and right here. How many edges are just on that top? 6. Right? Because it's a hexagon. Now going down, there's no vertices in the middle. So then if I go to the bottom, how many vertices are going to be on the bottom? Also 6. So 6 plus 6, there's going to be 12 vertices. Okay, for the edges are going to be where the faces meet. Okay, so I kind of think about like where you would see that crease, kind of. So since you have the picture, you can just kind of trace them. So I have 1, 2, 3, 4, 5, 6, just on that top. How many edges will I have on the bottom? Also 6. Are there other edges? Where are the other edges? In the middle, right? I've got how many here in the middle? Also 6. So I have 6 on the top, 6 on the bottom, and then 6 on the sides, which would give me 18 edges. And then lastly, the faces. Now I know I have a face on the top and on the bottom, so there's 2. And then how many faces are around the outside? 6, right? Because you're going to have 1 coming down from each side of that hexagon. So you got 2 for the top and bottom, plus 6, we're going to have 8. So we found the number of vertices, edges, and faces. Now let's plug those into Euler's formula just to make sure it works. So if I take the number of faces plus the number of vertices, it should equal the number of edges plus 2. 8 plus 12, 20. 18 plus 2, also 20. Now, what Euler discovered is that it also works if instead of looking at a 3-dimensional object, it also works for a net. Now, we talked about nets like the very first chapter this year. A net is if you take a 3-dimensional object and if you think about it as like a box and you were to unfold it and lay it flat. Okay? Now, here's the thing with nets. Whenever you're counting up the edges, vertices, and faces, some of them are going to look a little bit different, okay? So whenever we're counting up the faces, if you're looking at a three-dimensional figure, right, when you're looking at the faces, the sides, okay? Whenever you're looking at a net, it's going to be the figures, or the different shapes that you see, because it's going to be flat, okay? So all of you're going to count the number of figures that you see. The vertices are still going to be vertices. So remember, every time a side or a segment meets, that gives you a vertex. Okay, now the edges, though, where for the edges in a three-dimensional object, you're just looking for where the faces meet, kind of where those creases are. If it's laying down flat, what you're going to count is you're going to count every single segment. The edges are going to be all of the segments that you see. So to practice this, let's take this figure and let's draw its net. So to draw the net, this is what I kind of taught you at the beginning of the year. What I like to start with is the bottom. Okay, and draw the bottom first and then kind of unfold it from there. So if you look at this bottom shape here, what shape is that bottom? We'll call it a rectangle just to be safe. It might be a square, but just to be safe, let's call it a rectangle. So we're not going to draw it like a slanted rectangle because it's just a two-dimensional object. We're just going to draw it as a rectangle. Okay, so there's the bottom. Okay. Now what I would probably do is let's take this top and bottom, right, or the front and the back. Just fold them down. Now if you look at this front here, okay, as a trapezoid, where the wide base of the trapezoid is attached to the bottom. So when you unfold it, it should come out to a smaller segment that looks like that. Doesn't have to be perfect. Okay, so we've drawn the base, we've unfolded the front and the back. Now I need the sides and the top. There's a couple ways you could do this. What I think is probably the easiest, imagine if this was an actual figure made out of paper. If you took your scissors, and if I made a cut right along that side, and then just unfolded that here, okay, I would have this rectangle, and this rectangle, and it'd all be attached. So it'd look like this. I would have this rectangle, and then this rectangle, and then this rectangle. They may or may not be the same size. Not super important for what we're doing here, but we just kind of have the idea there. So what? This kind of looks like a t-shirt, doesn't it? Okay, now, to count up the number of faces, vertices, and edges, the faces are pretty simple. It's just the number of figures that you see. So I have the two trapezoids and the four rectangles, 6 faces. And that's the same as what it would have been in the three-dimensional figure. Now, the vertices, okay, the vertices, what you're counting in the net is you are going to count anywhere that you have a segment meet. So this side right here and this side right here, they meet right there. That's a vertex. That's a vertex. Here and here. Those are both a vertex. Here and here, here and here. All of these places where you have those segments meet are a vertex. And if we count all these up, we have 4, 8, 9, 10, 11, 12, 13, 14 vertices. Which, notice if you look at the figure, a lot less, right? Because the vertices here would be 1, 2, 3, 4, 5, 6, 7, 8. Only 8 of them. Okay? Now, for the edges, you are counting every single segment, which is kind of nice that we had to draw the net, because I think probably the easiest thing to do is just trace them, right? Here's 1, 2, 3, 4. If I draw down the sides, 5, 6, 7, 8, 9, 10. We have 11, 12, 13, 14, 15, 16, 17, 18, 19 segments there. Now, Euler's formula for nets is almost the same thing. The formula for solids is F plus V equals E plus 2. where the formula for nets is F plus B equals E plus 1. Why would there be a difference there? Why would there be maybe 1 less? I am changing dimensions. I thought this was kind of interesting. In a way, you're having to add 1 less edge, right? You're having to take the edges plus 2 up there, but I'm only having to add 1 extra edge here. Because if you look what happens in our two-dimensional figure, where I made that cut, if I were to count the edges in the two-dimensional figure, that would just be an edge, right? But when I unfold it, that edge is right here and right there. Right? I count it twice in a way, which is why you only have to add 1 edge. But notice it does still work. If you take the faces plus the vertices, it equals the edges plus just 1. It still works. Okay, your table of contents. I believe the next open page should be page 49. Page 49. Which means this is going to be glued into page 51. This is section 11.1, which is space, figures, and cross sections. All right, so one thing that you're going to be doing in your homework is just what we did up here. So a good chunk of your homework assignment is looking at a polyhedron, identifying the vertices, edges, and faces, and then verifying Euler's formula. So we're not going to do another one of those because those ones are pretty simple. So for these ones, we are just going to use Euler's formula to find the missing number. So let's say I have a polyhedron that has 5 faces. I don't know how many edges, but I know that there are 6 vertices. So I have a polyhedron with 5 faces and 6 vertices. I'm looking for the edges. As a reminder, Euler's formula says F plus B equals E plus 2. Faces plus vertices equals the edges plus 2. So just plug the numbers into the formula. There are 5 faces plus 6 vertices. I don't know how many edges. That's what I'm looking for. So we'll leave that as E plus 2. So 5 plus 6 is 11 equals E plus 2. So how many edges are there? 9 edges. And that would be true for any polyhedron with 5 faces and 6 vertices. It would have to have 9 edges. Okay, one more. If we do this time, if I don't know how many faces there are, but if there are 30 edges and 20 vertices, 30 edges and 20 vertices. So Euler's formula, we take the number of faces, which in this case I don't know, plus the vertices, which is 20, equal the edges, which is 30, plus 2. So we would get F plus 20 equals 32. How many faces are we looking at? 12. Excellent. Okay, that's some of what you're doing today. Just using the formula, get comfortable using that formula. Now these next ones are going to be kind of the same thing, except going to be given a little bit different information. So we still want to use Euler's formula, but we're always going to be looking for the number of vertices. But what's described to you is going to be a little different. So we're going to have to really use some visualization here. So number 1, let's say we have a polyhedron that has 1 hexagon face, 1 hexagon face, and then 6 triangle faces. 1 hexagon face. 6 triangle faces. Now, first of all, I'm looking for the number of vertices, so I'm not going to know what V is. But if I'm using a formula, and I have 3 variables, right, my F, V, and E, if I'm looking for one of them, I have to know the other 2. So I have to know F, the number of faces, and then I have to know the number of edges. Well, the number of faces, how many faces are there?
7.
Right, there's 1 hexagon face, 6 triangle faces, there's 7 faces. Now, to find the number of edges, I think probably the easiest thing to do is kind of picture what would this look like, and I think it'd be kind of hard to find the number of edges without doing this. And you don't necessarily have to sketch it out. If it helps to sketch it out, go for it, but I think you're going to at least need to kind of picture it. So first of all, you have 1 hexagon face. Okay, how many sides does a hexagon have? 6. Okay, and then 6 triangle faces. So that's kind of matched, right? 6 sides and then 6 triangles. So it's kind of, maybe kind of seeming like I've got the hexagon and then the 6 triangles. So if you did that and then kind of like folded it up, what would it look like? Yeah, it'd be a pyramid. Now, like I said, you don't necessarily have to draw it out. I'm not going to draw the whole thing out. But let's say we've got a hexagon. Bear with me. I know that's not a hexagon, but you get the point. 6 sides there. And then each side, right, is going to go up to the point, okay? So just so you, right, can kind of see that's what we're talking about here, okay? We need to find the number of edges. So let's start at the bottom. Remember the edges are where the faces meet? So at the bottom, how many edges would there be? Yeah, there'd be 6 on the bottom. But around the side, there would also be some. How many would be around the side? 6. Are there any edges at the top? No, because remember, edges are where faces meet, and the top would come to a point. The top would just be a vertex. So we've got 6 on the bottom, 6 around the side, we would have 12 edges. So we'll do the same thing we did above. To use Euler's formula, you take F plus V, so 7 plus V equals the edges plus 2. Oops. So we have 7 plus V equals 14. So we would have how many vertices? 7. Which, if we just kind of think through and make sure it makes sense, how many vertices would be around the bottom? Yeah, there'd be 6 points around the bottom, but where's that 7th one? At the top. At the top, very good. Okay, let's do this time, what if we have 2 pentagon faces, and then 5 rectangle faces. 2 pentagon faces, and then 5 rectangle faces. Okay, once again, to find this, we need to know how many faces and how many edges. The faces should be pretty easy to find. How many faces are here? 7. Now for the edges, this is where we kind of need to paint a picture of what this would look like. Okay, the other one I had 1 hexagon face, and then the 6 were going to be the sides. So you're going to kind of see a pattern here that we've got 2 pentagon faces, okay? And then how many sides does a pentagon have? 5. And then I've got the 5 rectangle faces. So those rectangles are going to be the sides, right? And this time, instead of coming up to a pyramid, this is going to have a pentagon on the top and on the bottom. So once again, it doesn't have to be like a perfect picture, but it would be, right, something like that. Kind of, yeah, you get the idea. Okay, so for the number of edges, start at the top. How many edges are on the top? 5 on the top, and on the bottom? Also be 5, but there's also 5 around the side as well, right? So how many edges? 15. So we're going to take F plus B equals E plus 2. So 7 plus B equals 17. So There should be 10 vertices. Okay, the last thing we're going to talk about is what's called a cross section. So if I would have been a little more prepared, I would have had like an actual something to show you, but I wasn't prepared. Wasn't prepared for this yet. I'm still looking around the room seeing if there's anything that I could use. So basically a cross section is if you take a polyhedron, if you take a three-dimensional object, and if you were to take a knife and just slice it, okay? The cross section is going to be the two-dimensional shape that's created if you like open it up, okay? Let's do this. Okay. So let's say I had this three-dimensional shape that looked like this. So it's kind of like a cylinder, but not really a cylinder, okay? And I were to cut it across, what would the cross section be? A circle, right? Okay. Now, if I were to take that cross section and instead of cutting it straight across, if I were to cut it in like a diagonal, would that change things? What would it be then? It would be an oval. So you have to kind of do a little bit of visualization here, okay? And also I will warn you that my drawings are going to be terrible on this. I can draw three-dimensional objects, but three-dimensional objects in a cross-section, not so much, but I'm getting better. So, okay, so let's try this. So number 4, what I want you to draw, let's start with a rectangle base, but it's not really, it's three-dimensional, so it's not really a rectangle, okay? And this is going to be a pyramid. So from each of these vertices, just draw it up to a point. I promise you this is not going to be perfect. That was not perfect at all. There we go. Okay, so we're going to do kind of picture a pyramid, okay? If you were to take a cross section, and I'm going to kind of show you before I actually draw it, because sometimes whenever I draw it, it kind of ruins everything. We're just going to like chop off a chunk just straight through to the back. Okay? So it looks something like this. So we're just going to take like a saw and go through like this. Okay? So kind of like this. And if I fill it in. Oh, that was way better than last hour. You should have seen last hour. It was not good. Not good at all. Luckily, you don't have to draw these today. It's just in the book. You gotta get the idea. Yeah? Kind of? Mm-hmm. Okay, so I want you guys to keep in mind that what we're picturing here is a pyramid, and if I just chopped off the top, okay, and I lifted up that top, the first thing that I want to make a point of, because I had this as a question last class. The last class somebody said, well, what are we looking at? Are we looking at the shape created by the top or the shape created by the bottom? Here's the thing. If I cut something in half, or not even in half, if I just cut something, these are going to be the same shape. This exact same shape, the exact same size, because they're going to fit back together perfectly. So it doesn't matter if you're looking at the top or the bottom. Does that make sense? Yes, in this case, the bottom three-dimensional figure is much larger, but I'm looking at the plane. Okay, the plane is going to be the same from the top and to the bottom. So if I were to just chop that off and then lift it up, what kind of shape would that be?
Rectangle.
Just to be safe, let's call it a rectangle. It might be a square, but to be safe, let's call it a rectangle. Unless you're 100% sure that all the sides are congruent, let's call it a rectangle. Okay, and then number 5, let's draw a cylinder. I'm a little bit better at drawing this one. And we kind of already talked about this one. That one's not good. There we go. Okay, now, let's talk about 2 different things here. And we're not going to actually copy down this first one. If I were to take this and just cut it straight in half, like think about a can of soup, okay, if I were to just cut it straight in half, what kind of shape would that cross section be? A circle. But, and like I said, we kind of already talked about this, if I were to cut this instead at an angle, okay, like, I'm getting good. You should see second hours because they were not good at all. And if you think these are bad, you should have seen second hours. These are much better. So if instead of I cut this at an angle, it wouldn't be a circle. What would it be? It would be an oval. Yeah. So be careful about what direction that you're cutting from.